So in this video we're going to go over how to convert from rectangular into polar form. We're going to do two examples, and one of them is going to have a subtlety. This first example is going to be easy. Then we'll do something that has a little bit more of a subtlety to it. But we're going to use all of the same relationships that we used in the previous video, the relationships that come from our background in trigonometry. And this says convert the point xy equals 0, 2 into polar form. So if you think about it, we could actually do this conversion without using any of these relationships that we see up here. We have the point 0, 2. The point 0, 2 is going to be up here on the y-axis. And converting into polar form should be pretty straightforward, because clearly the distance r is just going to be 2. The directed distance from the origin to the point is going to be 2. And the angle we can see is a special angle. It's one of the quadrantal angles. It's pi over 2 radians. So we could kind of quickly just say, hey, this is going to be in polar form r theta. This is going to be a radius of 2 and an angle of pi over 2. We could use the Pythagorean theorem, but it would be kind of boring. We could plug in 0 squared plus 2 squared equals r squared and go through the process of solving it. But if we have a quadrantal angle, then we're going to be able to convert directly into polar coordinates without even needing to use any of these relationships. And that's kind of the point of this example, is to demonstrate that you can get the result that you need without having to use the relationships that we know. This example will be a little more subtle. If I draw it in, this is my point in rectangular coordinates, and if I draw it in, it's going to be down here in quadrant 3. This is going to be at -1, -1. So I need this radius, and the radius I can get using the Pythagorean theorem. I know I have the two directed heights. I have a height of -1 and a directed width of -1. So popping our x and y values into the Pythagorean theorem, we would just get -1 quantity squared plus -1 quantity squared equals the square of the radius, and this is going to be equal to 2. And so the radius is going to be plus or minus the square root of 2. But we don't want to have to worry about dealing with the negated radius, so we'll use the positive radius. That's going to be the easiest thing to do. And then the only other thing we need to come up with is the angle with respect to the positive x-axis, because if we impose a polar coordinate system over top of this rectangular coordinate system, we would make the origin the pole. So we could get the angle without using any of these relationships. So I want to do it with and without using these relationships, because there's a subtlety in the use of the tangent of theta equals y over x that we have to be aware of without just blindly using it. So one thing we could recognize is that if we reflect through into quadrant 1, the reference angle for this angle theta right here, its reference angle is going to be the angle pi over 4, and the ordered pair 1, 1. So if it's pi over 4, it's going to be 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. I could just count my pi over 4s to get the angle theta. So theta equals 5 pi over 4. So one polar representation. There's infinitely many ways to describe theta, but one clean representation is, hey, the radius is the square root of 2, and the angle is 5 pi over 4. And the issue is if it's not a special angle. So if we consider, if it's either not a special angle or we don't recognize that it's a special angle, we're going to need to use the tangent of theta equals y over x. So if we do this, we go tangent of theta equals y over x, we're going to get -1 over -1 is going to equal +1. So the tangent of theta is +1. And then we would take the tangent inverse of both sides. So we would get theta equals the tangent inverse of 1. And the problem is the tangent inverse. If we remember from trigonometry, we had to restrict the domain of the tangent function to construct the tangent inverse function. So if you use the tangent inverse function on your graphing calculator or in GeoGebra Classic 5, which we've been using for this course, the calculator or the computer algebra system is only going to give you angle outputs on the open interval from negative pi over 2 to pi over 2. The tangent function is actually undefined at negative pi over 2 and pi over 2 because we get a division by 0. So the tangent inverse function, if you just blindly plug this into the calculator and you're not quadrant aware, the calculator is going to give you an angle between negative pi over 2 and pi over 2. And what we want to recognize is that the tangent of pi over 4, which is equal to 1 over 1, also equals 1, just like the tangent of the angle we're interested in. So the graphing calculator, if we plug theta equals the tangent inverse of 1 into it, the graphing calculator is also going to give us it's going to give us pi over 4. It's going to give us the reference angle. So the issue is, if we just blindly if this isn't a special angle, or if it is and we don't recognize it, and we just blindly use the tangent inverse function on our graphing calculator, we're not going to get the angle that we need. So we have to be aware of the quadrant we're in. We need to recognize that if we are in quadrants 2 or 3, that the calculator is going to give us a result in quadrants 1 or 4, and to get the angle that we need, we need to take the angle that the calculator outputs and we need to rotate it another 180 degrees or pi radians. So because of the quadrant we're in, the angle we're interested in is actually going to be the tangent inverse of 1 plus pi radians to rotate that angle around into the position we need. So then we get our common denominator by multiplying by 4 over 4, and we get 4 pi plus pi is 5 pi over 4. So we get the result that we need, but we have to be careful. If we just did this, and you can try this on your own for this example. If we just did this, hey, square root of 2, and then we did the tangent inverse of 1, and we put this as our result, we would get this wrong because the calculator would dump a pi. The calculator would give us the decimal approximation of pi over 4. It'd give us a number that was about 0.75-ish, 0.76 maybe, because pi is about 3, so that's about 3/4. So that's the subtlety. So anyways, converting is simple, but if you're forced to use the tangent inverse, you must be aware of the quadrant you're working in, because the tangent inverse may or may not give you the result that you need.